Wonderful. Good morning, everybody. I guess it's right on noon, so good afternoon as well. My name is Cameron Bailey. I'm a senior planner at the Metropolitan Council, and I've also been serving the region for the last few years as a solar advisor as well with the SolSmart Program, which has really been integral in helping us provide these series of solar technical assistance workshops and being able to provide them in a way where we're contextualized for our Twin Cities and greater Minnesota communities. What I'm kicking us off with is a little bit of why we're doing this series. And you'll see at the top, I'm referencing the 2040 Comprehensive Plan. So for those who have been engaged in the planning and municipal public service in any way in the last 3, 4, 10 years in Minnesota, you're well aware of where our community set their goals for the future in 10-year planning cycles. So what I wanted to go over is just a high level of what we saw from all of those plans, and that should connect why we're doing these workshops here today. So high level, by the numbers, we reviewed about 163 of the, I believe, 180 some odd plans from our cities, counties, townships, and our 7-county metro region. And looking at it specifically from a resilience, climate change, and natural resource perspective, this is how most cities, townships broke down resilience in their comp plan. So you'll see from the top down, about half had an explicit resilience or sustainability chapter or section in their comprehensive plan. 42 actually had a section or referencing how to integrate resilience planning and principles into their plans. And you can see on down the list, we have a healthy number with explicit energy plans for their cities, counties, or townships, even climate action plans. One of our largest areas being natural resource conservation and preservation. Then on down the list, then we get to implementation. And implementation, something that was fairly ubiquitous across all these comp plans, was revisiting our zoning and ordinances and our permitting and inspections processes to support the development of solar in our community. There we go. And that's why you see that right up there at the top. That was a pretty widespread goal of our cities, counties, and townships in our 7-county metro region. So increasing community-led use of renewable energy. And for a lot, that was at City Hall, as well as supporting and increasing the ease for private businesses and homes within our communities being able to adopt the use of renewable energy and quite explicitly solar in the vast majority of cases. And so other communities tied that also to greenhouse gas emission goals or electric vehicle adoption and infrastructure, as well as generally supporting greater energy efficiency. But the number one area of focus that we saw from our metro communities was by and far solar and helping increase homes and businesses' ability to adopt renewable energy, which is why we have enrolled a series of workshops this month. So we're kicking things off, today and tomorrow with permitting and inspections. Bill Brooks really being the national expert and leader in this space, really being lucky that we have really great partnerships across the council with SolSmart and with the Great Plains Institute and Green Step Cities, really allowing us to bring these technical resources and education to us here in Minnesota. The next week, we have a solar planning and zoning event with clean energy resource teams, the Great Plains Institute, us here at the council, and the Green Step Cities program. And later this year, as we continue to firm these out, We're going to be providing learning and workshopping sessions on how to use our greenhouse gas inventory, our greenhouse gas scenario planning tool, our tree canopy resource tool, and a green roof technical assistance tool. But where we're at today, kicking things off with solar permitting and tomorrow with inspections. And Bill Brooks will be our guide moving forward. So with that, I'd be more than happy to hand things over to Bill, unless Dave, you want to hop in there.
No.
Okay.
No.
Yeah, I'll show my screen here, get us going. And thanks, Cameron, for the introduction and going over some of the data you guys have. And it's exciting to see what's going on in Minnesota. And it's been a couple of years since I was up there for SolSmart. We've been up there a couple times to do various trainings. And so happy to be back talking to you folks virtually. And also want to encourage, as we get through going through the materials here, if you have questions, please put them in the chat, and feel free, Cameron or Dave, anytime you want to break in. I don't mind being interrupted, and be happy to answer questions as we're going through. And we'll get fairly far in this deck today, and then we'll wrap it up tomorrow, and then talk about inspection. So today we're going to focus on permitting. We may get to some of the examples, we may not. And then tomorrow we'll finish up the permitting guidelines and then talk about field inspections. And so let's dive in. I just want to move some things out of the way so I can see. All right, well, here's an old community map, and it's quite a bit more than this, but it's really just to give folks an idea that the SolSmart communities are all over the United States. I've been pushing to get Hawaii involved. We don't have them involved yet, even though they're a very big solar state, and Alaska, of course. So, but the continental United States is got a lot going on, and certainly you see a lot of activity in Minnesota and the central states. And so these guidelines are, for those of you who have not seen this stuff, hopefully provide you with an introduction that'll help you in getting to use these things. And for those of you who are using them, if you have questions or details, be more than happy to answer them. But the idea behind simplified permitting contracts is to have a format for jurisdictions and contractors to use to help them in providing the information that's necessary to for these relatively simple systems that are being used throughout the United States on residences and small commercial applications. And there are a lot of similarities in these systems, and that's what we're trying to work off of. A lot of these systems are starting to include energy storage and all, and even though this training we won't get into energy storage, I have been working on energy storage permitting process, which is very much like this. And so this is going to be focusing on the size, the electrical, structural, fire safety requirements. It'll also talk about structural requirements that are basically fill in the blanks in electrical review, to explain the electrical configuration, trying to keep it at a reasonably high level, getting the right information in. And when we're talking about residential projects, a lot of times, and this is for decades, I've explained that a typical PV installation is similar to an HVAC install and other things like that are very common in your communities. And So as we get into that, we definitely have code requirements, but these guidelines are not intended to explicitly or implicitly create any new requirements. It's really to show, okay, if you match these requirements, you are within what the code calls out. And in the residential world, it's going to typically be the International Residential Code, IRC, R331, and the like. And so we have the National Electrical Code, Article 6990 and Article 705. And I'm on the Code Making Panel 4 of the National Electrical Code. We just finished our first draft review of changes for the 2023 code. So I'm happy to have that behind me. But we're right in the middle of that process. And of course, the residential code and the building code and the fire code are starting their processes up for the next code cycle for the 2024 code. So the required information for permits, of course, most jurisdictions have some kind of an application process that includes things like the project scope, location, who's going to be installing the equipment, stuff like that. And then the second item would be a site plan showing the major components of the property, not necessarily to scale, but nowadays it's pretty easy to do that kind of stuff. But it's essentially to represent relative location of components and equipment at the site, where the solar panels are on the rooftop. Many of these are being rooftop installations, and compliance with any IRC setback requirements. And there shouldn't be any need for a separate fire service review. In fact, in the past, we've kind of included the fire service memorandum of understanding. That really has, the need for that has pretty much gone away because the IRC is explicit about it. In the past, the IRC wasn't really explicit about fire setbacks and things like that back in the 2015 version of it. And so now that the 2018 and forward is explicit, that information may or may not be needed in your jurisdiction. The electrical requirements, we have worksheets and standard diagrams that show things like the major components, modules, inverters, disconnects, things like that. And then specification sheets and installation guides for the major components. And this is where certainly COVID has helped a lot in, if we could say that COVID helped anything. It has moved a lot of jurisdictions that were not online to online processes, and kind of jump-started that process, kind of forced it in many ways. And so this documentation, which historically, like an installation manual for an inverter could be upwards of 300 pages. And most of those pages are programming details for the monitoring equipment and things like that, which has nothing to do with the safety of the product or anything like that. And if a jurisdiction required one of these manuals for every system or every inverter even, that could be a pile of paper that really is mostly unnecessary. So one of the nice things about having processes where PDFs can be shared, whether it's through an email format or through some online portal, it allows us to share these documents that could be quite large, but in a digital format, much easier to handle. So we're talking about a simplified process for small PV systems that simplifies and consolidates the structural, electrical, and fire review, eliminating the need for detailed engineering studies and unnecessary delays in that way. I am an engineer, and so it's not my desire to take business away from engineers. However, the building codes and the electrical codes are based on engineering principles, and to the extent that we can follow those and match those, specific engineering is not necessary, and the reality is the codes are specific in these areas. So it's not the intent to circumvent the engineering process, but really to talk about the similarities in these things, using the correct principles, showing that they're clearly compliant with the electrical and building codes, and that's really what we're after. So I like to talk about this as defining a box, and that meaning that if we have some constraints or boundaries a box, if you will, of the requirements for the system, we can go into a lot of detail on the engineering of that and really understand what's going on, and come up with basic guidelines that will work in every situation. And that's really what we'd like to see. So some of the constraints are not very big constraints or fairly high numbers. So, 15 kilowatt PV system is a massive PV system. You certainly have some of those in residential areas in Minnesota, maybe not so much in the metropolitan areas with rooftop systems, because you'd have to have an awfully large rooftop, but certainly in a little more rural areas. And I know even in the Minnesota area, even in Minneapolis, there are quite a bit of communities where people have several acre plots and things like that may have ground mounted systems where they could easily handle systems of this size. We're focusing on 1 and 2 family rooftop installations or structures of the same construction. So you do have small commercial construction that may be where it's taken over houses, retrofitted houses for dentist's office or what have you, and those same facilities could be treated just like a 1 and 2 family dwelling from the standpoint of structure and things like that. String inverters, DC converters, and microinverters are kind of the 3 major categories that residential PV systems are using these days and have been for several years. And then we have this eligibility checklist that we're going to go through. And the overall limitations on location in the program when we started out were some fairly robust numbers. Snow loads no greater than 60 pounds per square foot, and wind loads no greater than 150 miles per hour. Now, it's clear that in Minnesota you can get some high winds, but there are no places that I'm aware of that are above 150 mile per hour wind regimes according to the code. And from a snow load perspective, having done a little bit of research in Minnesota in previous years on this, I know that there is a small section of the very far north of Minnesota where it exceeds 60 pounds per square foot. But I think there's basically elk and caribou live there. Very few humans live there. But we actually have gone on and done some special work with high snow load, high wind load areas, particularly because we deal with stuff in southern Florida, and the same things that protect us from high wind loads protect us from high snow loads. And so they're even if you have folks that need information for that extreme snow loading areas, we can. But Minneapolis, we're good with 60 pounds per square foot. Here's an example of the high wind load areas, which would be the southern third of Florida, the Gulf Coast right on the water, and just snippets of the Atlantic coast area. Nantucket might be in that area as well. And then you see the blue line would be the northern parts of Vermont, New Hampshire, and the better part of Maine away from the water. And then the upper peninsula of Michigan, and it skirts right across the top of Minnesota. And Minnesota has that little blip that goes into Canada. I guess somebody had some property up there. I don't know the story. You guys could tell me why the United States has that little horn on it, but that's in a fairly high snow load area up there. So, but you can see that the vast majority of Minnesota is in the area that where these guidelines are just fine. Now, there are other areas in the country that we're not going to talk about, but in the western United States, you can see that the Rockies create all kinds of interesting problems in the Sierras and things like that, where we have high winds and high snow loads and things like that. Again, issues that are not a problem in the central United States, but just because of elevation, even in the Appalachian chain on the East Coast, we can get some very high snow loads and wind loads. So let's talk about these limitations, we mentioned the 60 pounds and the 150 miles per hour. We also say that it can't be an exposure D area. So when we're talking about the exposure of a piece of property, these are waterfront areas where the water is more than 1.5 miles, something like that, across. Basically open water in front of a house, a waterfront property would be exposure D. Exposure C would be kind of a house in the middle of a large field, away from trees and things like that. And then exposure B would be suburban areas and metropolitan areas where there's lots of buildings near each other, and so they kind of protect one another. And so, yeah, we're not gonna deal with waterfront properties. We're not gonna deal with steep hills. Now, there's not a lot of steep hills in Minnesota, but there certainly are some. And so, if there happens to be a steep grade of 5% or greater, somebody's got a house on top of a hill, you could have some extreme wind pressures related to that. Roof mean height of 40 feet or less. Now, a residence to have a 40-foot average height, which means the peak would be well over 45 feet, maybe even higher because of snow in Minnesota, is an extreme rarity. So this basically is just setting the upper limit at a limit that is extremely unique and would have to be some very large mansion to get up into that size range. The roof structure meets the IRC, which on older construction may or may not be obvious. And then there's no structural damage or modifications have been made. So a lot of this stuff is structural. And we'll kind of move through this. My intention is not to make you structural engineers or structural reviewers. We may have some structural people on the phone, and they'll love this stuff. The rest of you are going to be bored out of your mind. So we don't want to overemphasize it, but we just want to show that structural issues, as most people would think, are a big issue in areas like Minnesota where we get a lot of snow. And so we want to make sure that everybody understands that we have those things covered. Also, we have wind loading issues. So these are member attached requirements. And so this is a checklist. Array is set back from roof edges by at least twice the gap under the module. Okay. The gap under most PV modules that are sold today in the racking systems is about 4 or 5 inches off the roof deck. That's kind of the optimal height. And so if you're 4 or 5 inches off the roof deck, then you're going to be a minimum of 8 to 10 inches away from the bitter edge of the roof. And that's because of wind loading issues. That's there may be some benefit for icing and things like that, but it's really mostly wind loading issues why we require that, because of some high wind vortexes that happen right at the edges of roofs. We're also saying that the array can't be cantilevered over the perimeter anchors more than 19 inches. So often we will overhang our rails a little bit over the edges of our last anchor. And the last anchor, the perimeter anchors, are the ones that we really care about from a snow loading point of view, primarily. So it's the force of the snow pushing down and how much weight it's going to exert on the rafters or trusses that are along that perimeter. They're the ones that have to carry more weight than any of the rest, because the rest are sharing load among their neighboring anchors, whereas the perimeter anchors don't have anybody to help them. So that becomes the criteria, is how far can you cantilever over with a 60 pound per square foot snow load on top of it. And then we're mentioning that the gap under the modules no more than 10 inches. That's for wind loading, as well as the gap between modules being 1/4 inch on either side. So that's where we're. Those are primarily wind loading issues there. And then the rail orientation is run perpendicular to the rafters. So the vast majority of systems that we're using today, the rails are run perpendicular. So the rafters and trusses, of course, typically go upslope, downslope on a residential roof, and the rails are going to go crossways. That allows us to connect to as many rafters as we need to. in the process, makes it easy, and also distributes the weight nicely. With the anchor mount standoff spacing perpendicular to the rafters or trusses, we're not going to exceed 4 foot on center, and also the anchors in adjacent rows are going to be staggered where the rafters or trusses are at 24-inch or less on center. So in the Minneapolis area, for instance, your roofing is going to be either 24-inch on center or 16-inch on center, and you guys can correct me if I'm not right, but those are pretty darn typical. And so there's always going to be a rafter at 4 foot intervals, and then we'll show you some examples of staggered anchors where the anchors are attached to different rafters as we go to the different rows of rails, and that distributes the load perfectly evenly on the structure. All right, now the upslope, downslope anchor spacing, we'll get into, again, some examples to help you understand all this. The spacing of how far apart the rails are that the modules are mounted on is really a function of the module manufacturer's instructions, not the rail manufacturer's instructions. So the rail manufacturer is going to say, hey, they can handle any of these types of modules that are on the market. There's a lot of similarities in solar panels. And then the module manufacturers will say, well, if you're worried about, 50, 60 pound per square foot snow loads, then you have to mount the rails 3 feet apart or 3.5 feet apart. Those are typical numbers. And that you need to have about a 1 foot overhang on either end of the rail, and that will support the module most evenly so that the snow that collects on the panels will not damage the panels. Now I live in California, and I know people in California don't know anything about snow, and where I live, it never snows. But I just visited snow last week, and I went up to Lake Tahoe, and in the space of 2 days, it snowed 36 inches. So we can visit massive amounts of snow, and some of the highest snow loads in the world are near Lake Tahoe. And so snow loading is a real factor, and it certainly is in places like Minnesota where your accumulations tend to continue to collect over time rather than melt away and all that. So we understand that the snow loading is a major factor, and it is certainly in Minnesota. Anchor fastener spacing or types, I should say. Typical anchors that we're using for these fasteners that we're using for these anchors are 5/16 lag screws with 2.5-inch embedment. They tend to be about 4-inch long. Stainless or special screws that would lag into the structural members, the rafters of the trusses. And then there are other methods out there that manufacturers come up with multiple fasteners going into rafters or trusses. Could mean 2 1/4-inch fasteners that are spaced 3 inches apart, things like that. That there's several different manufacturers that might have engineering that's similar to the structural strength of a 5/16 lag screw with 2.5-inch embedment. Okay, so kind of a summary of the structural takeaway from that is that houses built in compliance with the building structural codes can support PV. So that's kind of a high-level takeaway. If we look at our building codes, the additional weight that a PV system would add to a typical structure is minimal, is negligible in how small it is. But we also pay attention to how we do anchoring on the roof so that it does spread the load out evenly for us. And we focus on a single layer of roofing. It doesn't mean that 2 layers of roofing is impossible, but it's certainly encouraged that a PV system be put on a roof that has a single layer of roofing Not only are there weight considerations with multiple layers of roofing, but there's also sealing concerns, flashing of screws and things like that, typical products that are used where they really want you to use a single layer of shingles and things like that. So it's certainly simpler to have a single layer of shingles. The modules mounted 2 to 10 inches off the roof deck. The array distributed weight is going to be less than 4 pounds per square foot. A typical average PV array for residential with the products that are being used today is about 2.5 pounds per square foot. So they're very light, and it's really more about how they're fastened to the roof and how they support the snow load that accumulates on them, that it's really the important issues for a place like Minneapolis. Typical rafter supports 48 inches apart or closer, and each anchor row mounted on alternating trusses or rafters. They meet the structural code requirements and represents most of the housing stock. Now, you're going to have older housing stock, certainly, in the metropolitan area and surrounding areas that well predates the structural requirements of the IRC. One thing that I would remind you of, having grown up in North Carolina where we have hurricanes, I like to consider that hurricanes were part of the inspection community. And so hurricanes basically wipe clean construction that is insufficient and not built to standards. And so the older homes and older buildings that have been there through 10 hurricanes, you don't even have to bother looking at them. Those things are built very substantially and built like a rock. And the ones that weren't built that way are long gone. And you could say the same thing for snow loading as well. If somebody were to build a substandard house in Minneapolis in 1926, that house is long gone. Its roof has imploded in on itself and whatever. But and you could argue with me on that one. But there's definitely housing stocks have changed. The woods that are used in housing stocks have changed. And in our structural commentary, we actually do talk about rafter spacings that are different and wood types that predate 1960, where they're very substantial, larger dimension lumber, better lumber, stronger lumber, and therefore should be considered for higher strength than the new construction requirements. So just because a house doesn't meet the brand new IRC code requirements and it was built in 1947 does not mean that it's substandard. Now there may be some substandard houses that are that old that are still standing, but that doesn't mean it's not a guarantee. All right, the next couple slides I just want to mention, and we're going to move on, but there are options in the permitting guidelines for low snow load and wind load areas. Of course, Minnesota would not be considered in that, and that's where half of California and the lower part of Arizona and New Mexico are in that category. And these guidelines get into those lower snow load, lower wind load areas, and again, they're not relevant. I'm just going to skip over them. Because I want to talk a little bit about sheathing attached, because sheathing attached systems are becoming more and more popular, and we'll see that over the next decade. Excuse me. We'll see a lot more of these. Again, we can handle 60 pounds per square foot snow loads with, and these are where the anchors are attached to the sheathing or the decking, the roof decking, rather than the rafters. And we can go all the way up to 60 pounds per square foot. We back down a little bit on the wind loading issues, where our roof mean height is a little bit lower, and that's for wind loading purposes. Again, that's not an issue for Minnesota. And then the roof structure, we'd say in general would meet the IRC, as we've talked about before. And if we have manufactured trusses or kiln-dried rafters, then we know we've got a structure that where the fasteners that are being used on the trusses are not going to give us any trouble. There has been some research done in the last decade that suggests that using green lumber has caused some issues with the fastening of sheathing, and the code is being revised, has been revised to kind of clean that up. But there is some housing stock out there where green rafters were used, and if the fasteners were number 6, then there could be some issues. That probably is not an issue in Minnesota, but again, you know, if you got a manufactured truss, they're kiln dried already, and of course, kiln dried rafters are probably going to be the vast majority of the products that are out there. There again, no structural damage or changes where somebody's modified structure, and then something called tributary area matters, and we'll go into that briefly, and I don't want to get a lot of detail on that. So sheathing attached for the most part, except for the high snow load areas, is going to work for us. And if we look at a sheathing attached system, here we're looking down on top of a house roof, and it's got a little gable thing off the front or whatever at the bottom right. But what I've shown here, and I don't know whether you can see my cursor, but the sheathing, when we build a roof, we start with full sheets of plywood or OSB, oriented strand board, at the edge of the house, and we work our way up to the top, and then whatever's left over, we'll cut the sheathing at the very ridge. Okay, well, in that process, measuring from the eave of the roof, we actually know where the sheathing is, and we stagger the sheathing as we go up for strength and rigidity and things like that. And so in that process, we know that if we're mounting our anchors 2 feet from the bottom edge of the roof, we're right smack in the middle of a 4-foot by 8-foot sheet of plywood, because these plywood are installed in what we call, if you're talking about paper, a landscape fashion. Okay, so if you're in that area there and you're close to the edge of the roof, that's the strongest part of the sheathing. Now, it's virtually impossible for a system to stay in those bands of strength all the way up the roof unless it was specifically designed as such. And so this is just showing how this row of anchors, these little dots are rows of anchors across the bottom here. I don't know whether you can see my cursor. And then the second row is in bands of strength. The third row is not in the bands of strength. The bands of strength being the middle 16 inches of the 4-foot dimension of a 4x8 sheet of plywood. And so that's getting into how strong is a piece of sheathing to be able to support both in downward force for snow and upward force. Actually, the upward force is the thing that's of greater concern for bands of strength and for sheathing. Again, not as big of an issue in Minnesota because you're not in super high wind load areas. But so that's a little bit about bands of strength, and then we have rules about that, and that's just to give some context to where we can put anchors in a sheathing type attached system. Now, the reason we talk so much about this, and maybe this is too much to talk about, is that sheathing attached systems, like I said, are going to become more common, and they're far simpler to install. And because they're far simpler to install, there's a higher likelihood they'll be done correctly. One of the challenges that we have with member attached systems, where we're having to put a fastener in a 1.5-inch wide target, and the code wants us to put that fastener in the middle third or middle half, I should say, of that 1.5-inch space. You have a 3/4-inch target to which to get an anchor into a roofing member, and that's a very small target. And there's some guys out there, some folks out there that can do that every day perfectly, really well, thousands of times, and there are others that can't. And so one of the parts of inspection is to actually, if you have attic access, is to go as an inspector and poke your head in the roof and see if the fasteners are coming out the side of rafters or broken any rafters, because that obviously will weaken them. And so, you know, these sheathing attached systems really have the advantage of doing away with that particular problem. now we're getting some other problems in, or we're trading some issues for other issues, but those issues I think are pretty straightforward and simple. So if some of our anchors are not in the bands of strength, then what we do is we put some stipulations that the edge of the array is no closer than 3 feet from the edge of the roof. So it means it's keeping the array within a wind zone 1, requiring a tributary area of 9 square feet or less, which is basically each anchor is in charge of handling no more than half a module. And we'll see, and I'll show you an example of what I mean by that. If we are going to, I'll go back to that. If we're going to if we're not going to pay attention to bands of strength at all, and when I mention bands of strength and talk about that middle 16 inches being stronger, the middle 16 inches is about twice as strong for wind uplift than the edge of the sheathing. So twice as strong doesn't mean that the edge has 0 strength. It just means that it's half as strong. And so with that, we're not going to want to go above 120 miles per hour. And we're going to focus on wind exposure B, which would be residential, suburban, metropolitan areas in general, not houses in the middle of a field or on the waterfront. Okay. Now, if we pay attention to bands of strength, we can be a little more liberal in our exposure characteristics, and we can handle a little more weight and things like that. So that's just what that's talking about. And then our anchor sheathing connection has an allowable stress design uplift capacity of 166 pounds under short duration loading, which corresponds to an ultimate tested uplift capacity of 520 pounds. So when we do testing on these anchors, they have to be able to handle an ultimate strength of 520 pounds of uplift force, and we take that number and we divide it by 3, and that's sufficient. We also have the general statement on all our structural stuff that if any structural item can't be checked off, the building official may require the installer to provide structural calculations and or details that are stamped and signed by a design professional addressing whatever the unchecked item is. So as we go through the checklist, if there's an item that's unchecked, then they can look at that, and maybe it's a fairly simple evaluation that they can do and just write a letter that says that in this particular situation, that item is covered by the overall design. Let's talk about the electrical system requirements for a moment. These are quite a bit simpler than the structural, and I've been working on the electrical side of this stuff for over 30 years and my entire career, and so things have gotten a lot simpler and more straightforward over the years, and a lot of it's been based on the fact that we have listed equipment for virtually every piece and part that are used in PV systems, including the mounting hardware, the inverters, the solar panels, any of the electronics and stuff like that. So that's number one, is that the major components, the electrical components are all listed and identified for use in PV systems. The array mounting system is going to be grounded according to the grounding standard UL 2703 certification for bonding and grounding, and so that makes it much easier. It's a very simple way to ground and bond PV systems, but they have to have that certification. And so there are probably 5 dozen products on the market today that have these UL 2703 certifications. And so it's just a matter of verifying that that certification has been achieved for that module and rail combination. So the way that works is that the rail manufacturer provides certification that they've tested it and had it certified to UL 2703 for X number of modules. And so, you know, there's some large companies like Unirac and Iron Ridge and Snap and Rack and all these different companies that manufacture rail systems will have literally hundreds of modules that have been tested and evaluated with their products. And these, when using their mounting system, will actually bond and ground the rail system as one electrical unit, and we can put a ground lug on that entire array section, and it's fully grounded and don't have to worry about any separate parts and things like that. We can also alternatively put separate UL 2703 grounding devices on each separate metal part and piece, but that's a lot more difficult and generally more costly. And so even though it is an alternative, it's certainly harder to install and ultimately harder to inspect too. The PV array consists of no more than 2 series strings per inverter, so that's talking about the electrical configuration, and no more than 4 series strings, that's the electrical configuration going into each inverter, and that's pretty much the products that are on the market today that represents those products. The field wiring, because of some changes that have happened in the last couple of electrical code cycles, we can actually, in the past we used to say minimum size was number 10 conductor. Now we can go one smaller than that, which is number 12. The higher the number, the smaller the wire. It's weird unless you're an electrical person and it's natural for you. So we're talking about number 12 wire, PV wire or manufactured cable being used in the source circuit wiring, and then any field installed wiring, we're going to be using THWN-2 or XHHW-2 or RHW-2, and no smaller than 12 gauge there. Output circuits we really don't have anymore in residential, so C is kind of a non-issue. And then the circuits on the buildings meet the requirements for controlled conductors in 690.12. 690.12 is the code reference for rapid shutdown. So rapid shutdown has become a big deal in the last couple of code cycles, and it's really designed for improving the safety of firefighters working around this equipment up on a roof. And so most of the systems, a lot of the systems that are being installed today would be, are installed either with microinverters, DC optimizers that are on each module or pairs of modules, and then what has become popular over the last year or so are switches that mount on each module, and so each module can be turned off with a remote switch. And so these are all aspects of improving the fire safety for firefighter safety. And then we have a new standard that's UL 3741, which is for PV hazard control. And so there are now a few products on the market now that have special design. Many people have seen on TV and other places the Power Roof product from Tesla. That is one of the UL 3741 products that's on the market today, and there are a few others out there. Again, we talked about total inverter capacity being 15 kilowatts, and these products are normally installed on load side connections. However, if they are using a supply side connection, then they would have to meet the requirements of 705.12a for supply side installations. Equipment is rated for the maximum DC voltage, and then we talk about the ASHRAE mean, extreme, minimum dry bulb temperature. So I give you a reference here for that mean, extreme, minimum dry bulb temperature, and that is the old permitting guideline that I did for the Solar America Board for Codes and Standards 10 years ago or so, and that document is still on the web, and the temperature resource is still on the web. And let me see if I can tab over to that real quick and show you. Let's see, let's open this up here. And here we have the Minneapolis International Airport, and the mean extreme minimum dry bulb temperature according to ASHRAE is minus 28 degrees C. So that would be used in this document as the, if you were doing it in the Minneapolis area. If we're choosing another area, we pick another area. As you move up, as you move north, obviously it gets a little bit colder, minus 31 degrees C. We keep moving north, Well, let's go to Duluth. We've done some things in Duluth, and Duluth is actually about the same as Minneapolis because it's near the water. And then we go way up north here, and again, you can get into some really cold temperatures. I don't need to teach anybody from Minnesota about cold temperatures. I always like to make fun of people in California that complain about the cold temperatures when it's 48 degrees outside. And I said, well, why don't you look on your phone and bring up Minneapolis, Minnesota, for instance, and just see what it is there right now. And it comes out at -10. And said, shut up and put on a sweater, whatever. So table 690.7 is the values for temperature adders, and so those temperature adders would be used in this little simple worksheet here in figuring out how much the cold temperatures is going to increase the voltage on a PV product, because PV semiconductors increase in voltage in cold temperatures, and we obviously have to take that into account, particularly in places like Minnesota. So your increases in voltage are going to typically be about 20% in the wintertime, and you do definitely have to take that into account for DC converters if the system has DC converters, and then also for a series group of modules that are going into various inverter inputs. And so you could have several inverter inputs and a different number of modules going into each input. And so we have a way of just filling that out in this little worksheet. And then we have standard electrical diagrams that we'll show you in a minute here before the end of our training today. So let's talk about an example. That example would be a 7.5 kilowatt central inverter system with American Solar. These are all fictitious companies here. 360 watt modules with a 7.6 kilowatt inverter and a racking system that's UL 2703 rated. The roof pitch is only 4 and 12, fairly low pitch, and the house was built in 1988, tract home kind of thing. So let's look at what that might look like. Here is a sheathing attached system, and we see the bands of strength shown in there, and we see setbacks. Now we're required to have 1 3-foot wide setback from eave to ridge. We see we already have that here. This whole area over here counts as a exit path if necessary, but we also have a whole area of roof access over here if we needed it. So this is not a particularly large system. The code today, the residential code, would allow us to take this all the way up to 18 inches from the ridge of the roof, since this array is less than 1/3 of the overall roof area. So the IRC residential code, 2018 residential code, would allow us to go within 18 inches of the roof. That was unnecessary on this system, and we are able to stay within 36 inches of the peak of the roof. So that's the sheathing attached system. Now here's the electrical system, showing some of the multiple sets of modules, and they would have to have some rapid shutdown device to shut the modules off. And then this is shown for Alexandria, Virginia. I apologize for that, but instead of -12, which would be for maybe the Virginia area, we put -28 in there for Minneapolis, if this is a Minneapolis system. And what that's going to do is that's going to increase the maximum voltage number over here of the array from 495 volts up to probably 525 volts, something like that. Now, the only reason that would be an issue would be if the inverter was rated for only 500 volts, that would be a problem. This particular design would put it over the 500 volt number. However, 600 volts is a more common maximum voltage for inverters. So a 600 volt inverter would be fine, 500 volt inverter would not be fine. So that's a good case in point why temperature matters. And so let's see, rather than going into a whole nother example, I just wanted to stop here. We got about 5 minutes left and pause and see if we had any questions. I know I've covered a lot of material here. See if anybody had any questions that they'd like to ask about something maybe I said that didn't agree with, didn't like what I said about Minneapolis being cold, something like that. I'd like to just answer some questions if we have any questions. Cameron or Dave, do we got any questions out there?
No questions I see yet.
Okay. Well, so hopefully this is relevant. In fact, let me ask a couple questions. I don't know whether, is there a hand raising option here in this one? Every one of these options are different in different programs. I know we have a chat window and all, but it would be nice to know what are some of the jurisdictions that are represented. Cameron, maybe you know some off the top of your head because you know the folks that registered. Could you fill us in, maybe help us understand who all we have online? And
Yeah. We have a lot of folk who work as permitting and inspection officials for cities themselves, being, big cities like Minneapolis, St. Paul, some of our first ring suburb communities, think of like a Hopkins, a Falcon Heights, a Golden Valley, then some of our secondary and tertiary suburban ring communities, thinking more of like an Edina, Lake Minnetonka, Blaine, Cottage Grove, and then our further out townships with some rural center communities. And I know with some of our smaller communities, that's where we start to get more private kind of contractors that are contracted by cities, generally like kind of clusters, to help support permitting and inspections needs for a few different communities actually clustered together.
right.
So across the gamut from pretty rural, like 2.5 units per acre, if not 1 unit per 10-acre communities, up to, over 100 units an acre. So
right.
pretty broad across the gamut in terms of what PV systems look like in the metro, and what I think various folk on this call will see within this webinar see in their communities.
Sure. No, that's very helpful. Yeah, so that's a pretty broad spectrum, and we talked a lot about like exposure B, which is like a suburban environment where you've got subdivisions and stuff like that, and I'm sure many of your communities have those types of housing areas. But you've got in the rural areas, you've got houses that are going to be certainly by themselves. Now, you can still have a house in the country be exposure B because it's near a wooded area. So normally you've got to be at least 100 yards from tree lines and things like that. And so houses that are kind of out in the field, exposed, with no trees around them and things like that could be exposure C. I know that if I lived in Minnesota, I would want some tree protection from the winds and the cold. And so I think it's very common to see houses in rural areas even put in trees if they're not located near forested areas and things like that. So I just want to explain a little bit about that exposure B and exposure C. And of course, your structural people, if you do have structural experts in your communities, they can give better feedback on what they view as exposure B and C in the communities and all. Whereas waterfront's pretty straightforward, that's where you're right on the water with a large body of water. Now we know that Minnesota has lots and lots of lakes, maybe 10,000, and the vast majority of those lakes, a lot of those lakes, I should say, are not even a mile across, and so they would not put you automatically in exposure D, but several of them are quite large. And so the waterfront houses on those very large lakes would fall under exposure D. And of course, Duluth, that might be a large lake there. So
we had one question.
Sure.
So we had asked, does SolSmart have a template to use for this?
A template for, yeah. So let me, in fact, I kind of went off of it when I was looking at that right here. But this is the website, solsmart.org/permitting. And so there are several pages under, this is the landing page for that. And the templates are on here. And these are documents you can download and you can walk through, and it's got videos about basically walking through the process. But here's step 1, gathering required information for the permit. Step 2, structural PV array mounting requirements. And step 3, electrical system requirements checklist. So we have a checklist on here, and these resources are available, and I'm available to help any communities that are working through these things, that have questions. We have commentary documents that are part of this website that you can download and explain the permitting worksheet. So great question, and thanks for that. And I think we're out of time today, and we're going to pick this up tomorrow and finish out our permitting stuff, and then talk about field inspection. So with that, I will turn it back over to Cameron and Dave. And is there anything else you want to do before we sign off?
I just want to quickly piggyback on this resource page, Bill and Dave, in that we also have a lot of communities in the metro who have already adopted the current or some previous version of these permitting sort of guidelines or applications. And so also feel free to please reach out to me if you want to connect with some of the communities adjacent to yours who may have already started down this path in previous years when we've hosted these education sessions.
Yeah, I'd like to add one thing. So I'm gonna like to share my screen here for a second just to wrap up. So, you know, what Bill, I think, was showing was sort of on the sort of the back end side of, you know, reviewing, you know, how to, you know, deem what system qualifies for streamlined or simplified permitting. We also, SolSmart just recently released a sort of a template for public facing about what are the required permit submittals and steps for a community's process. And so that is a credit to reach SolSmart designation. And so we put together a template checklist that, you know, that a community would use and adapt to meet their permitting process. And so this is online on the SolSmart website. And so, you know, this is something that you would adapt to your community's process. So, you know, if you require electrical or building permit or a zoning permit, you just sort of tailor to that. And we've listed out some of these required documents that Bill has gone over for a simplified permit system. So I think this is a great resource. And so that is on the website, and we can send around these resources to all the folks that have attended, send links to those.
Great, thanks, Dave.
Yep. But yeah, I guess we can wrap it up. Thank everybody for joining, and we will see you all tomorrow.
Excellent. Yeah. Talk to everyone tomorrow, and think about any questions you might have had related to today's presentation. Be happy to address those tomorrow.
Great. Thanks, y'all.